Okay, right? Okay. Okay, so I'm going to do this part of the stochastic processes. My name is Sanjib Sabhapandit. So Abhishek, I think what he has done in the morning, so he had started with this random walk and then taken different limits. So I'm going to stay in the continuous space, continuous time. So what is the simplest stochastic process you can think of in the continuous time, continuous space? Diffusion, right? So what is diffusion? I mean, you must have heard, you know, you have seen this thing in colleges or something, right? So what is diffusion? So diffusion is something, so if I just, for example, release some perfume here, right? So this perfume has different molecules. So they are not going to go straight towards you, right? So suppose they go straight towards you. How long does it take for you to smell the perfume after a release? Imagine that they just go straight. So time will be proportional to the distance, right? If they are going straight to you, right? But this perfume molecule, they will not go straight to you because there are air, they are going to hit it. So this kind of motion, imagine that you have some perfume molecule here and you are somewhere there and I'm releasing from here, right? Just consider one molecule. So it's not going this way, right? Even if it starts this way, because there are air molecules. So what will happen is it will have some kind of motion like this, right? So this time, the straight path, let's call this, so this distance is L, right? So straight path, the time taken by the straight path is proportional to L, right? So this path, this time is proportional to L. So what do you think of the actual time now by this perfume, like when you get the first smell or when you get the smell? This time will be larger than that one or smaller than that one? So it will be larger, right? Because I mean, like suppose you guys are coming from IISc to here, if you just take the direct bus, you are going to reach faster. But you just take bus, go first to Bangalore airport and then go somewhere else, is going to be slower. No? So this time will be, you expect that this will be larger than L, right? So this is something called diffusion. So this you have seen in everyday life, right? You see this thing like, for example, sometimes when this sunlight comes through a small hole, you see this dust molecule, dust particle, right? How do they move? So they move some kind of this zigzag motion, right? So they don't just go straight. So they go straight in one direction and then they go somewhere else and then. So this diffusion is a very general phenomena, okay? And there's something called diffusion coefficient. I'm going to come into it at a time. And that, of course, the diffusion coefficient, whatever this we call it D, so that will depend on the phenomena you are describing, right? So there's no one fixed diffusion coefficient. So if I put some perfume here, it will be different. If I put a ink in water, it will be different, right? So this is something depends on the process, right? So I'll start with a particular kind of diffusion process. So that's called Brownian motion, okay? So that's also a diffusion process. So what's a Brownian motion? So this is, if you suppose you take water and you, so this is your water, and you take a small particle, right? This small particle of size about micron. Okay, so it's, let's say this particle size is about 1 micron. Right? So what's going to happen to this particle? It will again diffuse because these water molecules are hitting this particle. So this particle will diffuse. Right? So corresponding to the diffusion, there is a diffusion coefficient D, and what we are going to do, that we want to know what is this diffusion coefficient for this 1 micron particle, let's say in water. Right? This is something you should, I don't know how many people have seen Brownian motion. You have seen? You have seen? Okay. So if you just take a microscope, for example, and just okay. So these people who have seen Brownian motion, what is the experiment you have done to see this one? How did you see the Brownian motion? No, but have you seen? Okay, so what is the experiment you did? Okay. 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 So how big is your template, and how do you put, how much water you put? Okay. So who has done the experiment? Okay. Yeah. Okay. 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 How much do you put on the slide? Okay. 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 So now can you describe why do you put this cover slip on top, and why just not like look at it with a big beaker and just put in the microscope there, look it under the microscope? So the reason is that, so although I'm saying is that if you take a beaker, big pool of water, for example, if I take this bottle and put a particle there, this particle will have some motion. But this motion, all of that motion is not due to Brownian motion if you take a large pool of water, because there will be temperature gradient, right? So that temperature gradient will make you there will be a lot of microcurrents in the water, right? So there will be lots of convection current, and there will be some random currents, because here it will be some current, here, there will be current here. So those current will be dominant than actually the Brownian motion in that, right? That's the same reason when you see a dust particle, for example, through this thing, it does a diffusion, but that's not a Brownian motion, because there also is just that because there will be some small microcurrents of air, right? That's still a diffusion, right? So if you want to see diffusion in this thing, so what you usually do, you just take a cover slip, you take a whatever the glass plate, put a very tiny amount of water, just a 1 drop of water, okay, and then you seal it nicely, so that if you have a little bit of water, you don't expect much water this temperature variation. You cover it so that there is no this evaporation, right? So you do all these things, and then whatever the motion you see, that's the diffusive motion. So the Mr. Brown saw what was, he saw something, okay? The original experiment actually the scientific experiment what did is somebody called Jean Perrin. Okay, he actually measured scientifically like what is a diffusion. I'm sure he has taken care of all these things. Okay, right? See, whatever this Brown saw is basically, so see, even if you see something underwater, you'll see things moving. I don't know whether he put a little bit of one or he put a large amount of one, but he didn't make any quantitative measurement, right? He also didn't give an explanation for this process, right? So this explanation for this process was given by Einstein, right? So this explanation was given by Einstein and some other people, okay, which was known later. So okay, so now this you have this diffusion coefficient for this Brownian particle in water, and this one we want to express in terms of some other quantities of water, right? Some other properties of water, some macroscopic properties of water, right? So what are the macroscopic properties of water? You know this one. So this water has some temperature, right? So it will have some temperature. So if you have high temperature, you expect this particle to move more vigorously, right? Because you expect that more molecules are heating in a short time, right? Then there is the viscosity, or let's call some viscous coefficient, right? So now what Einstein did is basically relate this diffusion coefficient to these quantities, right? So this is what we are going to do. So this is called so now imagine that this, instead of one particle, you have now many particles, right? So you have many particles, and it's a dilute suspension, so that there's no interaction between these different particles, right? And it's under some force. So there's a force F acts on each individual particles, right? For example, this force may be gravity, right? Or it may be, if these are charged particle, you can put under an electric field, right? So it can be any force. So let's call it F, okay? Since it's a closed container, so what do you expect? So initially, when we apply the force, okay, this force will act on this particle, there will be some movement, right? Bulk movement. Of course, this individually this particle will be always keep moving, but as a whole there will be some bulk movement, and after some time it will come to some kind of steady state, right? You will not see any bulk movement. So although at individual level each particle are moving, right? So you will not see that if I just look at, let's say, these 5 particles here, you will not see that they are just going together somewhere, right? So it will stop because it's a closed container, right? So if, of course, if it's an open container, it will keep moving, right? So therefore, if there is no bulk movement, that means there is no net force on the, so suppose I just imagine that there is some particle there, some volume of particle there, there is no net force on that volume, right? Because if there is a net force, it will force this particle to move, right? So therefore, so let's do force balance. So what kind of forces are there? Everything is taken care of in F. So this is the external force, right? So you call it gravity or whatever, it's there in the F, right? So one is, of course, if I just assume there is a dilute suspension, there is a pressure of this suspension, right? So what is it called? Osmotic pressure, right? So if it is dilute, then what is the osmotic pressure? Just follows the ideal gas law, right? So this one, pressure at some position x is given by times the density. So therefore, if I consider, imagine that there is a small volume here. So what is the force per unit volume? if there is a pressure variation, see if pressure doesn't vary, then there is no force, right? But if there is a pressure variation, then there will be force, because on this imaginary volume, one side will have more pressure than the other side, right? So you can just look at what is the pressure here, what is the pressure here. So then you know the force. Force is just the pressure times the area, and you finally divide it by and you know this distance, so you divide it by the volume, then you can find out what is the force per unit volume due to pressure. This will be minus it's just the negative of the pressure gradient, right? So that's the force, and this one, of course, you can substitute that one. There's also another force, to this external force F. And what is this force? So this F works on each particle, right? Each particle experiences a force F. What is the force per unit volume? Is just the number of particles in that volume. So that means F times how many particles are there per unit volume? It's a rho. Okay. But now, as you have said, that there is no net force on that volume, right? Because if there is a net force, that volume means that this whatever the particles there within that volume, they will move as a whole. But if you wait for a long time, then you will not see these particles are moving as a whole. So there is no net force. Okay? So therefore, the total force must be equal to 0. So then what is the total force? This plus this. This is the force. Where is the viscosity here? We'll consider, but I'm saying that you have to put it in the proper form, right? Where are you going to put the viscosity here? What is the viscous force? Suppose I just put a particle in a water which is fixed. What is the viscous force on the, it's not moving. What is the viscous force on the particle? Right? So we have to see when it comes, right? So you have to put there is viscosity of course there, that's why we want to relate all these things, but you have to put it in the correct form, right? So is there any other force? Viscous force is not an external force, right? Is it an external force, viscous force? Viscous force is something response to the external force, right? So is there any other force acting on this packet? So potential is infinity here and 0. So it's like an infinite force when she hits the wall. It's like this one, no? This one. When you hit, it's infinite force, but otherwise no force, right? Is there any other force? So this is the total force acting on the particle. So what is the total force now? Minus kBt del rho del x, I have substituted E this one, plus F times rho x, and what we are saying is that this must be to 0. Right? So we are also going to do another way of, we are going to look at the system in another way. So when things move, there is current, right? So current is what? Just the number of particles going through some area per unit area, right? So imagine that again you are looking at some position and you are looking at particle movement through that position, right? So that's the current, no? How many particles are going per unit area per unit time, right? So now current, again, if this thing is steady state or equilibrium state, right? The current must be equal to 0 because if things are not moving as a whole, right? So then current must be again equal to 0. So what are the currents now? So what are the current? There is an external force. So if you have a force, let's say you have a steel ball in water and you put force, this ball moves, right? So what is the velocity of that ball? It's just terminal velocity, right? So what is the terminal velocity? Force by whatever your friction coefficient, right? So if it is a spherical ball, then this is 6 pi eta a, right? But otherwise, whatever this, right? So that's the terminal velocity. Now, each particle, suppose moving with that terminal velocity, right? So what will be the current? What will be the current? Density of particle into velocity, right? So this is just v times density of particle. So this is just f by gamma times, right? There's also another current here. As I said that if I release some perfume here, it's going to go towards you at some point, right? So suppose I just have a wall somewhere here and I'm just looking at some cross section and I'm counting how many particles are going through this one per unit time. So that's also some kind of current, right? So that's called the diffusion current. So what will be the diffusion current? So the particle will go from high density to low density, right? So that's proportional to minus, right? So it depends on the gradient, negative the gradient, and this proportionality constant, I just make it equal, so that's called the diffusion constant, right? So this one is right, it's called the Fick's law, right? So this is true for any diffusion, right? If there is a diffusion current. Is there any other current? These are the two current. Again, the total current must be equal to 0, right? So what is the total current? Let's just write down minus d del rho del x plus so now we have two equations, one is this one and one is this one, describing the same quantity, namely rho. And both are equation for rho. The same observable, the density I am just looking at, right? So therefore, these two equations must be the same, they must be same. Right? So if I say that they have to be same, then what does it mean? So this KBT here has to be equal to gamma times D, right? So this one is basically a relation which expresses this diffusion coefficient in terms of the temperature and the whatever the viscous drag of the system, right? Okay. So this one is, so I'm giving a homework problem. So this is now the same equation, right? So now, if I solve this equation, okay, can I solve this equation or no? It's just a first order equation, right? So everybody know how to solve a first order equation, right? So solve this equation and find out what is rho of x. Okay. Find rho of x. Okay. And if I say that the system has a equilibrium, so you have to find out what should be the sign of f, okay, and what is the answer? So what is the answer you expect? Huh? See, what I am saying is that now, see, this D depends on the problem to problem, but D, what does D mean actually? Right? So we are going to see what is a D. Okay. So now, so what here I have done is this diffusion coefficient D I have expressed in terms of the temperature and this thing. So now what I am going to do, diffusion constant in terms of microscopic fluctuations. Okay. So for any diffusion, the diffusion constant is defined by this equation, right? It says that, okay, if you have a diffusion current which is equal to minus d times del rho del x, right? So it's just the proportionality constant between the diffusion current and the negative gradient of the density. Okay. Right? So this is how you define the diffusion coefficient. And so this is called Fick's first law. Then if things are not destroyed or things are not created, then there is a continuity equation, right? The second one is continuity equation. So what is a continuity equation? So this one I am doing everything in one space coordinate, but you can actually easily generalize to any higher dimension, right? So it just says that del rho del t is equal to the negative divergence of the current. So that's minus del del x of. Right? So this is continuity equation, or also called Fick's second law. Okay. So now if I just substitute this J diffusion from the first one, so we have an equation which is called, this is the, there's one derivative, then another derivative coming from there. So this is what you have, this diffusion equation, right? So this is a general diffusion equation, it's for any diffusive processes. So as you saw in the previous class, that random walk also, if you take a proper scaling, basically you look at a slightly far away so that you don't, you coarse grain space and look at like a continuum time. In some suitable limit, you get this equation, right? So this is the, so what is rho here? Rho is the density, right? So density of these particles, let's say. So I have released lot of them here, and they are non-interacting, and I'm just looking at how many particles are there in a given volume per unit volume. So that's the density. But instead of the density, suppose I just look at one particle. You have all these particles, but instead of that, suppose I just put only one particle there. So what's the equation that particle should satisfy? So now instead of this density, if I have just one particle, so what do I have to ask? So probability density, right? So so here I'm asking, what is this rho? Rho is a function of x and t, right? So what is the meaning of rho? So suppose this is the equation, it says that, okay, if I have, let's say this is my space, right? And initially, let's say you just release your perfume here, all the particles are here, so you say, okay, you just release all this thing here, right? So density is 0 on this side and all the particles are concentrated here, right? So this equation says that how will this density profile evolve in time, right? It's going to spread, right? So at some point it will have some density. So density still it will be low here, but it will keep on increasing. If I just fix on some position, you expect that you get more and more smell, right? And this equation describes how does this density profile evolve. But if I have a single particle now, so instead of that, so now I'm taking a single particle and I'm just releasing from here. The single particle again going through this zigzag motion. So what is the question I'm going to ask now? So I'm going to ask, what is the probability that if I just, so now instead of this density profile, now I'm just releasing a single particle. Suppose I just start from some position, okay, call it 0, doesn't matter. I'm some position x. This time I'm just releasing a single particle. Asking what is the probability that I observe the particle between x and x plus dx, between a small this thing at time t. That's the probability, right? So it says now, instead of this density, I have a probability T of xt dx. This is the probability of observing the particle between x and x plus dx at time t, right? So therefore, if I divide it by dx, it's again become a density. It's called probability density. It's not that density. So this one is called probability density function. So this is okay, same as E of xt. So this is called probability density function. So what is the equation this P of xt should satisfy? Why? So why should it satisfy the same equation? So since particles are non-interacting, so this rho also you can think of it, okay, either the full density or the fraction of particles, right? So you can just divide this rho, you can either think of it like a number of particle per unit volume or number of particle per unit volume divided by the total number of particle, right? So that when you integrate rho, in that case it will be 1. Okay. But otherwise, see now, imagine this experiment. These particles are non-interacting, right? So how are you going to compute? Suppose you are doing a computer experiment, simulation. So how are you going to do this experiment? You release a particle at the origin, let's say, and at time t you see is there a particle there or not. So what you do is you make bin in your space, right, of let's say size delta x, and you just put a first particle, and at time t see is there a particle there. If it is not there, then you put 0, but the particle will be somewhere, so you put 1 there, wherever the particle is. But since you have to compute this, so you cannot just do one realization, right? So you're going to do realization, right? Going to put again another particle and another particle. Let's say you do n realizations. So now you are going to do n realizations. So after n realization, what will happen? There will be some particle in every realization. There will be only one bin. You will put a 1, and other places you will put 0, right? If you keep doing that, what will happen is sometimes it will be 1 here, sometimes you put a 1 here, 1 here, again you put a 1 here, right? Because the same space you will observe this particle many times. You will put a 1 here, 1 here, 1 here, like that, right? And finally, to compute this one, what you are doing, you are just counting the number of ones in that space, okay, divided by the number of realizations, and you are dividing by this delta x. This is what you are doing. But since these are non-interacting, does it matter that you do this experiment like one by one, or you put everything together, right? So it's the same if I just take all n particles together and just run it together, right? So when you do all these n particles together, that gives you the density, right? So therefore this density is same as the E of xt if you normalize it to unity, right? So if you just say that this density I divided by the total number of particles. So therefore this P of xt must satisfy the same equation. So P of xt also satisfy the same equation. But D is the diffusion coefficient, right? But we can also derive this equation, right? So we are going to now derive this equation starting from the microscopic dynamics, right? Okay. So this equation we have just written down from the observation that this equation must be same as that other equation, right? Now we are going to derive this equation. From so what we are going to assume is that, okay, these particles are moving there. So what kind of motion this particle has? So this guy, let's say this is my time and this is my space axis, and I can start this particle, let's say somewhere from 0 every time. And suppose I just look at one trajectory. So how does the trajectory look? Okay, it's basically that one, but I'm now drawing in one direction. So what will happen is that at some point so this will basically look something like that, right? Because time is going on, this particle sometimes go like that. So this will look something like that. I'm just looking at some small time interval of delta t, and I'm just looking at where is the particle, right? So it will be some random curve, looks like that. Now what I'm going to assume that this movement, whatever the movement here and whatever the movement here, they are unrelated, uncorrelated. They're independent. This particle going this direction. The next direction wherever the particle going is independent of the what is the motion previously. Right? So this is called, this property what I'm going to assume. So what I'm going to assume is that basically whatever the jump the particle is going to take, that jump is independent of all previous histories. Right? So that's a property which is called Markov. Right? So this is called a Markov property. I think Abhishek had mentioned about it when he talked about this master equation, right? So you can write down this master equation when this process is Markov or Markovian. Okay. So if I assume this property, then what I am going to do, suppose I am just looking at some time t, right? Or let's call it t plus delta t. So then t must be here. So I want to write down what is the p of x t plus delta t. It's the same way Abhishek wrote down the equation for the random walk, right? It's almost similar. So can you tell me what would that be? So imagine that I'm just looking at a step of delta t, right? So I'm at x at time t. So then I have to say where was the particle at time t, right? So that's same as the probability that particle was at some position nearby, right? In this random walk case earlier, what was the equation? Do you remember? X plus 1 and x minus 1, because those are the neighbors, right? It either comes from x plus 1 or x minus 1. So here, where does it come from? So it can come from anywhere. So in some places, let's say x minus delta x at time t. But then it has to jump from x minus delta x to x within that time delta t. Right? Probability that it jumps from x minus delta x to x. So in this random walk case, those are the p's and q's, right? It jumps with probability. Okay? So that's the some probability it jumps by amount delta x in time delta t. Is that all? So sum over all delta x's, because there are only two, sum over all delta x's, so I have to basically integrate over all. Right, that's all. Now, this one you can expand in Taylor series, right? So what you see is that, so this is equal to p of xt minus delta x del p del x plus you expand this. And now, so what is the random variable in this line? In this line, what is the random variable now? This delta x, right? For a fixed x I am looking at it, right? For a fixed x, what is the random variable? The delta x, right? So now this one, so what does it give? P of xt times, so this is an integral with respect to delta x. It just comes out of this thing. And this is a probability density again, because it's a probability that it jumps by delta x. So if I just integrate to it, it just gives me 1. So this one gives me P of xt The second one, so I'm assuming that in this case there is no external force or something, so it's a homogeneous, right? So this integral is, so del p del x anyway comes out, this integral is delta x phi times d of delta x. So phi, I'm assuming that phi is symmetric, right? So what I'm assuming is that phi of minus delta x is same as phi of delta x. It's a symmetric function, right? From which side it's coming, it doesn't matter, right? So then that integral will give me 0, right? Because delta x, phi is a even function. So this is 0 minus 0 plus that one. That one, okay, let's just write half. So what is that integral? I have this integral, okay, let's say minus integral plus infinity delta x square phi of delta x of delta x, and this whole integral times higher order terms, right? So in principle you should calculate all the higher order terms, yeah, but okay, we'll see why we are just keeping it here. So this is what it is, right? So now you can see that I can take this thing on the left hand side and divide by delta t. So then what we will have, and take limit delta t going to 0. Okay. So what is the equation you are going to get? In this term you are going to get something like, okay, limit delta t going to 0, 1 over 2 delta t, that integral times this one. All the higher order terms, right? But now, again this equation must be same as this equation, right? Because we argued that this we just got from the argument that, okay, this just satisfies the same equation. This is the equation we have written down and we have derived something. So this must be equal to that equation. So what does it mean then? So D is whatever is this one. So this has to be equal to D. Okay. And what is this object inside? It's just the variance of this one, right? So it's just the second moment, right? So D is just this one. So therefore T is equal to, what is this? Delta x square expectation value divided by 2 delta t limit delta t goes to 0. Right? Now you see that in that equation, of course, there are no other terms, right? So now you can go back and look at what happens to these other terms here. So what is the order of these terms, other terms? Everything is divided by delta t, right? Now you see that delta, you have taken a limit where delta x, whatever that, this guy goes to 0, because if you take this to 0, this has to be also goes to 0, with this with this kind of scaling, right? So you see that delta x square goes like delta t. So delta x goes like square root of delta t. So it just says that, okay, your space goes like square root of delta t, right? So now what is the order of this term? Anyway, here all the odd terms will be 0 by symmetry. So now it will be like delta x to the power 4, right? So delta x to the power 4 will be like delta t square. You have divided by a delta t, so it's still delta t. So in the limit delta t going to 0, that goes to 0. Similarly, all higher order terms, right? So therefore, all the higher order terms, they go to 0, okay, in this scaling. Okay. So therefore, what we have got, so we have got one relation of the diffusion coefficient in terms of temperature and friction, and we have got another expression of the diffusion coefficient in terms of the microscopic fluctuations. Okay. So, so now it's an exercise. So now, given that P satisfies this equation, okay. So how do you solve this equation? I think you have already solved this equation, right? There are several ways to solve this equation, and I'll not do it here because Abhishek has already solved that equation, right? So this is, so he gave you which way to solve. One is Fourier transform, one is whatever. So solve it one more way, which is slightly more complicated, but it's useful because you learn one more technique, right? So you solve this equation. So earlier you took a Fourier transform. So this term went away and you had a first order equation. Now I want you to take a Laplace transform with respect to time and keep space as it is. Right? You know Laplace transform. What is a Laplace transform? Everybody knows, right? So Laplace transform solve it before next week. I'm sure in David Dink's lecture you'll have a lot of Laplace transform. So maybe just get familiarized with Laplace transform. So what is a Laplace transform? The Laplace transform is, so it's a now variable which is bounded from one side. So this is, now let's call E tilde x s, that's the variable corresponding to time, and this is given by 0 to infinity dt e to the power minus st of. You'll give a boundary term, right? So what is the equation you'll get? Let's quickly do. So let's just write down the equation. So what you are going to do, you are going to multiply this by e to the power minus st and integrate it over time. So this side, of course, there is no problem because this is space and you have just integrated time. So it just, this one becomes whatever p at e tilde hat. So the left hand side, you have to find out what is this term. So now what you are doing is 0 to infinity dt e to the power minus st del v, right? So what do you do? Because you know only this object, so you just do integral by parts, right? So when you do integral by parts, so what is the answer? How do you do integral by parts? So you integrate one guy and differentiate one guy in the next one, but what is the first term? So first term will be e to the power minus st e xt 0 to infinity minus the differentiation of, okay, minus 0 to infinity dt, differentiation of this term, it will give you a minus s, and then integral of this one. So then e to the power minus st e of xt, and that's same as this object, right? So what you have is, so this one now, so you are going to assume that at, okay, so see, at t goes to infinity, this is 0, right? But there is still another term which is coming from minus p of x0 plus s, right? So you know this equation now. What is the equation? This minus this term comes to this side as right. This is the equation you have to solve. So I'm sure everybody knows how to solve this equation, right? How do you solve this equation? You have solved these kind of equations, no? Similar equations earlier, right? You first solve the green function. You first solve the equation for delta function initial condition, right? That means that you assume that at time t equal to 0, the particle is at some position x0. So you solve for p of x0 is equal to delta of x minus x0. And once you solve this one, then you can write down the general solution, right? So this will give you the propagator, and then you have to do the back transform. Okay. So how do you do a back transform? So it looks like a Fourier transform, but slightly complicated, right? Because it's just a one-sided. Now this variable goes from 0 to infinity. So how do you get p of xt? Is given by okay. Okay, this is more or less like the Fourier transform. E to the power minus st becomes e to the power plus st. E to the power st p of ds, right? But this integral is now in the complex S plane, and there is a 1 over 2 pi I, that's like this 1 over 2 pi in the Fourier transform, right? So this contour, you have to choose this contour such that you take some number c, real positive real number c, okay, and this goes along this one, I infinity to plus I infinity, such that all the singularities of this function p lies on the left side of this contour. Okay, so whatever the singularities of this one in the complex plane, it just lies on the left side of it. Okay, so this contour is called Bromwich's contour. Okay. So this is slightly, I guess, more complicated than the inverse Fourier transform, but you should learn, right? This is a very powerful trick. Yeah. So what then after this equation came? So what this Jean Perrat did is, so now we have two expressions for diffusion coefficient. One is this one, and one is this one. So now you can measure this one. Okay. So okay, just before that I want to tell you one more thing. So now, so this diffusion coefficient I have defined by this equation, right? But now you can check that. Now you can go back here and actually you know the solution of P of xt, right? What is P of xt? That's a homework assignment you are supposed to solve. But let me just write down the answer. Can you see that side or is just the end? You cannot see, okay. See now, so when you solve this equation, I think Abhishek has already given you the answer. So if you solve for an initial condition, let's say P of x0 is equal to delta of x minus x0, right? So then P of xt is given by 1 over square root of 4 pi dt for dt, right? That you can just solve. Fine. So this is the Gaussian distribution, right? So now compute the moment. For example, suppose you compute this x minus x0 whole square expectation value at any time. So what you will find is given by 2 dt. So that says that this diffusion coefficient is given not only by this limit delta t going to 0, because experimentally this is a difficult limit to take. So this is true at any time, and that's because of this Gaussian property, Gaussian measure, okay, because of this equation. So now you know that it's true at any time. So now you can actually take some finite time and measure this left hand side quantity in experiment, right? Because you don't have to look at a small time, you can take any time. You can measure this, divided by time, you have a diffusion coefficient, right? Now you go there, and now this k is given in terms of, you know, this gas constant, right? What is the gas constant divided by the Avogadro's number? So gas constant people have measured early in experiment various ways, very distinct. So then what you can find out from this one, gamma you know, now d you know from this experiment. So what you can measure is the Avogadro's number. So you can measure the Avogadro's number, and this was I think one of the first precise measurement of Avogadro's number. And he got Nobel Prize for this work in 1925. Okay, yeah. Yeah. What is phi? Phi is the probability of jumping, right? So what we say that we do not need phi, we just need the fluctuations. Okay. So this is given by whatever the phi is, it will be given. The diffusion coefficient will be determined by that. No. This one, this is the definition of your expectation value, right? So this is what I am just writing down. I am not calculating. So I am writing down this one and I am defining, so this, whatever this thing has to be equal to d. Okay. Now we are saying that, okay, so now we know this object. So d is basically given in terms of fluctuation. Okay. Now you can compute that fluctuation from this equation. So this one just says that d is basically related to fluctuations, right? And you see that same scaling you have when you go from the random walk to the this diffusion equation in this Abhishek's class, right? So now, yeah, so now given that equation, you can basically solve and you will get the answer. So you can also write down the general solution. So this is for a again check that for general initial condition, right? So suppose let's call P of x0 is P0 of x. So for general initial condition, the solution is linear superposition of this single fixed initial conditions, right? This is single point initial condition, right? So this is given by plus infinity dx0. So x0 is my p0 of x, and now p of, so this one, let me call it, so this solution is for a specific initial condition, right? So this one, let me call it z of xt given x0, 0, right? So this is the solution for a delta function initial condition, and this is given by x0, xt, x0, 0. So this one is called the propagator, right? Like in quantum mechanics. No? So this one is so it says that okay, if it is x0, it goes there. This is the probability of going there, and this is the probability of finding the particle in x0 at time 0, and you just add up all the probabilities, right? So check that for general initial condition, this is the solution, right? So when you compute this using your Fourier transform, check that that is the solution. Okay. So now I have another 20 minutes. So this is a description of this motion in terms of probabilities, right? I'm not looking at individual trajectories, right? It says that probability means basically it's like a given an ensemble of trajectories I'm computing thing, right? So probabilities are not for single trajectory, right? So now I want to look at this process at the level of single trajectories. Okay. So how does the trajectories of this process look like? How do you describe the trajectories of this process? Okay, so I had the trajectory somewhere there. Okay, let's just come here. So now to go back to your question now. So since we have solved this equation and we have gone to there, right? So what is phi of xt now actually? Phi of delta x, right? So that's essentially this object now, because it says that the t need not be large t. If it is a small t, delta t, this equation is still valid. And this just says that, okay, what is the probability of a jump of delta x? So it just says that, okay, e to the power minus delta x square by 4d delta t, right? So phi is your Gaussian, right? They are saying that now we are going to assume that this phi is also Gaussian, okay? So it's a process where phi is also given by Gaussian, same distribution. So the question is the scale, at what scale we are looking at, okay? So this is a scale where we are looking at, we are scaling the space as the square root of the time, okay? So in that scale, there is something called central limit theorem. That if you, so what is happening? Basically, you are just particle and hitting by every other particle, right? So it's just a sum of forces. So now, of course, if you exact distribution is not Gaussian, but if you look at a specific scale, so in that scale it is Gaussian. Okay. and only in that scale this equation is valid. So this equation will always, so the process we are looking at it in that scale, right? That's why we are getting this diffusion of equation, right? So once you have this diffusion equation, it is basically at the scale where you have neglected all the other distinct terms. So what I'm saying is that, when you define D, saying that your process is defined by this kind of thing, right? So you have looked at the coarse grained picture. So if you look at your perfume molecule individually or at a very small scale, it will not satisfy this equation, right? So it's at a scale, it's at a coarse grained scale you are looking at it. So therefore, at that scale, so you have to also be careful what is the meaning of this actually delta t going to 0 limit. It's not simply just this thing. So there is a scale at which you are looking at, and at that scale, that process is described by that equation. And if the process is described by that equation at the scale, then you see that delta x, I'm just saying the jump, right? So it's just the same, basically it's just the same what I probability of going from x minus delta x to x in a time delta t, okay? So it also is given by the same probability density function, right? But I can go and look at a very small time scale, small space scale, and I'll see it's something completely different, right? So now, let me just give a description, Langev description. So that's the description at the level of trajectories, right? So let's look at a trajectory of a particle as a function of t, and imagine that you are just looking like this experiment in Jopera, but you are looking at again a small interval of time, okay? Every small interval of time delta t, you are making a measurement and just writing down the x coordinate. So how will it look? So this particle, okay, every time you can set, wherever you look at, you can just set the origin to be 0. At time delta t, you will see the particle somewhere. You don't know what is going on in between because you are not looking at in between. After again some time delta t, you will see this particle somewhere there. After some time, you will see this particle somewhere there, somewhere there. So you will have something like some discrete point on your graph paper. Right? So now, since you don't know what is there in between, so when you plot, you just join them by straight line. Right? So what you do, you just join them by straight line. So now you can ask what is the properties of this trajectory. This you call it delta x, right? This delta x is different every time. Delta t is fixed, but this delta x is just this jump size. It goes from here to here, that is delta x, then it goes from here to here, these are my delta x, right? So you can now look at delta x by delta t. So this is the slope. So these are the slopes, right? And you expect that these slopes will be random, right? So you call this slope some random number. It's of course depends on delta t, right? If you make a delta t distinct, it will go probably slightly larger distance, right? So it will depend on delta t, and it also depend on at what time you are looking at. This time is now discrete in terms of this delta t, right? So although I am writing t, it's a discrete time defined in terms of this delta t, let's say t is like delta t, 2 delta t, 3 delta t, so on, right? This is a random variable because delta x is a random variable. Right? Because delta x is drawn from phi of delta x. Right? These are the sum. And we are assuming that phi of delta x is Gaussian. Right? We are saying that okay, phi of x is given by Gaussian. So therefore, this is random. Right? So this is a random variable, it's a noise. So what we call it? A noise. Okay. So now we want to find out what is the properties of this noise. See, this guy is related to delta t or delta x. So it's basically related to the properties of delta x. And delta x is a Gaussian. Delta x is Gaussian. So this is also Gaussian. Right? Because it's just the same variable, you just scaled it. So therefore, this one is okay. It's a Gaussian. So you know that Gaussian distribution, it needs only two this thing. One is the variance and one is the mean. So what is the mean? What is the mean? 0, because mean of delta x is 0. So this mean is 0. So this is basically delta t. So this is equal to 0. Okay, now we need to look at the variance. What is the variance? Also, okay, before looking at the variance, correlations. So let's look at this object, delta t at some time t and some time t prime, where t is not equal to t prime. These jumps, I said that they are uncorrelated, they are independent, right? Whatever the jump here, the jump there is different, right? They are not correlated. There is no connection between these two jumps, right? That's because of the Markov property, right? So therefore, if these things, so that's same as the expectation product of the expectation value of these two, and that will give me again 0. So now, so these are uncorrelated in time, and now what about at the same time? Now I look at this object. So what does it give? This one, square root of this, square of that. So this guy, delta t square, delta x square, expectation value. Now, delta x square expectation value is given by 2d delta t. So therefore, 2d by delta t. If you want to generate these trajectories, you are going to write down this equation, because delta t is fixed, so you just evolve by this equation with a noise which is Gaussian with mean 0 and variance goes like 1 over delta t. Okay. Now we can take, if you want to write down a continuum equation, so this is how you do the simulation actually. If you do a simulation, this is what you do. You can actually, okay, for the simulation now you can simplify a bit, and what you can do, since this noise has a variance delta t, that means the strength of the noise is like 1 over square root of delta t, right? So therefore you can define another noise, let's call it eta, which is what do I want to write? Okay, let's go, yeah. So what it means is that you can call it 1 over square root of delta t times eta. So you can just take out this factor outside, right? So now this is a noise. So now this guy is 0, eta square is 2d. In fact, you can just take out now square root of 2d also outside. And this is just 1. So now we have an equation actually very simple when we want to iterate. What is the equation? The delta x is given by delta t goes there. There is a square root of delta t. There is 2d. So it's square root of 2d delta t times this eta of t. And this eta of t is a Gaussian random variable with mean 0 and variance 1. Okay, so this is mean 0 and variance equal to, this is a variance equal to 1. So this is how you are going to do a simulation. So let's go back to this old equation now, and we want to write down this equation in a continuum limit. We are going to take this delta t going to 0 limit. So I put it in the quotation because okay, we do not know what is this, how mean, in the sense that what we are going to do is we are going to assume this delta t smaller and smaller and just looking at this particle, this thing, but how small? Okay, so that we don't know yet. So although I am writing delta t going to 0, but so how small we don't know yet. Okay, but assuming that okay, we are just taking delta t to be very small. So if delta t goes very small, so left hand side becomes this one, of course, is just the definition of your dx derivative, right? Dx. This right hand side, now I want to basically, so this is equal to something like this is the noise I am going to write. So now what is the properties of this noise? As I said, the mean is still 0, and variance is given by this. But this one, what is this object actually? If you look at this object, 2d by delta t, limit delta t going to 0. So, or let's look at this object, delta t e prime going to 0. As I said that if t and t prime they are not same, it's still 0, right? So this is still 0 if t not equal to t prime, and if t and t prime same, then 2d by delta t, limit delta t going to 0. So it just blows up, it becomes infinity. Okay, but suppose I just integrate this function over one of the variables. So what do I get? So when I integrate it, time step it of this thing of delta t. So when I integrate, so what I mean is that you can suppose you just, this guy will put it here. One of the variable, any variable. Suppose you integrate. So integrating means actually you are integrating in discrete step of delta t, right? So this is actually a summation. So what you are doing is basically we sum over this t prime at the step of delta t. For all these guys where t is not equal to t prime, this object is going to give you 0, except at one point where t is t prime, so that's going to give you 2d by delta t, but then there is a delta t, so that's going to give me 2d. So what kind of function is this? It's just 0 everywhere, blows up at one point, and the integral is finite. It's just a delta function, and the strength of the delta function is 2d, so this is 2d times delta t minus t, right? So this is how you go from here to there. So this is your, now of course you don't have to write this delta t here. No, you can just say that, okay, I can just forget about this delta t, and I said, okay, this is my equation. Noise, the correlation is given by this, the mean is 0, same as this, 0, and this is a Gaussian white noise. This is what we call it. Okay. So we should come back to this one. Maybe the next class we'll come back. What is the meaning of this delta t going to 0? Because you know that it's a classical particle, right? I mean, there's nothing else, and you know that all classical systems are governed by one equation. And what is that equation? Newton's law, right? So I can write the Newton's law for this equation, this system. And what is the Newton's law? This is not Newton's law, no? Right? So this is not Newton's law. So what is the Newton's law? So Newton's law says that this is equal to all the forces. So what are the forces? One is friction and one is this noise. Okay, noise. Let me just take another symbol. Let me just call it so this is my noise. This is somehow related to this, the same noise but with some other strength, okay? And that equation doesn't look like this one at all, right? So what you will see is that, okay, so suppose I just divide this equation by gamma, so what we have is m by gamma dv dt equal to minus v plus 1 by gamma, right? Or let's look at it in a different way. Okay, this is the equation. So this is the equation for a full system. So this is some noise which is proportional to this one with some strength, that we'll see what is that strength. But this equation is different from this equation, right? And you know how to solve that equation. Again, homework, okay? Solve this equation because it's just a first order equation. So you have to just find out the integrating factor and just solve it. Okay? So this one, it gives you a time scale, right? Because this is velocity, dv by dt, this is time velocity. So this is m by gamma is time, right? So m by gamma is a time. So if gamma is large, the time is small, right? So this gives you a time scale. And this is the full description of the system. You can solve it and actually find out all the moments, try to do. And then if you're looking at a time scale which is larger than this time scale, so this is the viscous time scale, right? This is the time scale at which, so suppose you forget the this part for the time being. Right? Just forget about this part. You solve this equation. So what is the solution? So Vt is equal to V0 e to the power minus, right? So if you plot, so this V, so it's something like that, and this is like m by gamma. So this is a time scale after which basically it forgets its velocity, right? This is the inner. So after that, it doesn't matter what velocity this started with, it forgets that, right? If you're looking at a time scale, which is your delta t, when you say delta t going to 0, if you look at that delta t is much larger than m by gamma. That's the time scale you are looking at. Okay. If you look at a time scale where delta t is larger than m by gamma, so then this description is good. So this one is called overdamped Langevi equation, and that one you can call it the underdamped Langevi equation. Yeah, there is some question. Yeah. So I have told you what is the limit at which I am looking at this particle. So it just says that I am looking at these trajectories. I'm looking at these trajectories and I'm finding the slopes. And it says that the slopes are random with mean 0 and variance is given by that. And this is the limit delta t going to 0. You have to keep in mind what is the meaning of this limit, but this is a well-defined meaning and you can do. So physically you have to keep it in mind what is the limit at which you are looking at. As I said, if you are looking at a time scale, physical system with time scale less than this one, that equation is not correct. That equation is correct when you are looking at a time scale which is larger than this time scale. Then that's a correct description of the system. Okay? Mathematically, although it looks strange that it says that basically the slope velocity is random everywhere with some blowing up this thing, but it's like a well-defined problem. You can do all mathematics this thing, there is no problem.
Physically, the velocity is not defined.
Physically, I told you what it means.
So velocity like this by dt.
So velocity, the physically says the velocity, what you say velocity is the inertial velocity, right? It says that this velocity, actually you should solve this equation now. You solve this equation, find out what is the mean velocity. What is the, so now given that, okay, now this equation means that this term should not be there, right? So that is, so this term, when I ignore this term, that's the description given by this one. So you know now what is this chi, right? So it's basically your equation is dx dt is equal to 1 by gamma times chi. You know the strength of this chi, so you can find out, right? So now you actually now put the actual thing here. This should be actually, okay, let me not, okay. So this should be, the strength should be square root of 2 gamma kbt, this thing. And now you solve, find what is V average, what is V square average as t goes to infinity, and that should give you your, so that should give you a Maxwell distribution, Maxwell velocity distribution, and this should be basically give you the, what do you call it, equipartition of energy, and half m kv. So what you should give is that half m kv square is half kbt, right? So it says that this is a time scale at which the velocity is equilibrated. The velocity is equilibrated at a faster time scale, and now you are looking at how does the, you look at the position. That's the equation not for the velocities. That's the equation for the position of the particle. So that equation describes how does the position of the particle evolve in time. if you're looking at a time scale which is beyond this one. So if you want to describe the velocities of the particle, how does the velocity of the particle this thing? So you have to use this equation. That's the equation which describes the velocity of this thing.
I can't write v equal to x.
That's correct.
But I mean here it seems wrong because v is
No,
multiplied here.
yeah, so that's correct, but that v is basically that same v I have showed you. This velocity I have drawn, that I have ignored what is happening here because I can't see inside. And if this is what you are defining v, that's not the actual velocity of the particle, right? This basically says that this is some distance divided by time, okay? But that's not the instantaneous velocity of the particle, right? Yeah, because the velocity is what it says that they evolve at a faster time scale. They equilibrate very fast. On the other hand, position, they evolve by something else. For example, in this case, there is no equilibrium, right? Because there's no, I have not put a potential. So you see the solution. So solution evolve at all time. It's a Gaussian. So what is going to happen is that is initially you start with that, you start with that, start with that. Okay. This. So it keeps evolving. So there is no equilibrium. So equilibrium means that the distribution depends independent of time. On the other hand, the velocity distribution, if I solve this equation, so I have not told you what is the crumpling equation corresponding to this one, but if I write down the equation, so maybe I'll do it tomorrow or something, then you will see the velocity will equilibrate much faster. And it should have the Maxwell distribution. Any question out there?